Okay. So what I have here is I've drawn some lines in this quadrant of the imaginary and real axis, and we're saying we're sort of mapping out what happens as pole locations move around. So what I've drawn is based on the three parameters we just talked about: percent overshoot, So, percent overshoot, time to peak, settling time. I've drawn lines of constant value. So what happens here is, this is a line of pole locations with a constant time to peak. So if a pole is anywhere on this line, that pole represents a system with a constant time to peak. This line too. Every pole along this line represents a system with a constant time to peak. And in this case, the time to peak represented by this line is smaller than the time to peak represented by this line. So the further up your pole is on the imaginary axis, the shorter your time to peak is. Here, these lines are settling times. We have TS2 and TS1. These represent constant settling times. Here, TS2 is actually a lower settling time than TS1. So, the further your poles move to the left here, the smaller your settling time is. Generally, a smaller settling time is good. Generally, a smaller time to peak is good. So typically, we want our poles to be further up and further out. What have I shown here, though? These are lines of constant percent overshoot. So the lines of constant percent overshoot emanate from the origin. You can guess, well, just looking at this, do you think this line has a higher percent overshoot, or do you think this line has a higher percent overshoot? When you make this guess, think about what you know. What would a line that's vertical, what would this line represent? What would this line represent? Think about that when you make your answer. Pause it, take a minute, talk amongst yourself, find an answer. Which is the smaller percent, which is the larger percent overshoot? Welcome back. Yeah, this one is the larger percent overshoot. Imagine for a second. This line keeps going further this way, becomes the imaginary axis. This is 100% overshoot. Imagine if this line keeps moving this way. This down here is no percent overshoot. That's critically damped once it gets down to there. So what we're dealing with here is being able to visually look at the location of a pole and seeing how the location of that pole affects the system response. Again, in general, we want poles that are far away from the origin, so we minimize our time to peak and minimize our settling time. But even far away from the origin, the position of that pole, closer to the imaginary axis, closer to the real axis, is going to determine the percent overshoot that we see. Okay. Now, what does it look like though? What would the response of these systems look like traveling along these lines of constant time to peak and constant time to settle and constant percent overshoot? Okay. So let's consider this case where we have poles as poles move in this direction. So we're going to call this 1, 2, 3. What should we see? So in this case, what is this? These are lines of constant settling time. So as these poles move up, they're staying along the line of constant settling time. But as they move up, we should see a shortened time to peak. As they move up, we should also see a greater percent overshoot. So what do these look like? They look like this. So this first response here might look something like this. The second response here might look something like this. This last response here might look something like this. So this response 3, 2, 1. 3 has a greater percent overshoot. 3 has a greater percent overshoot. But 3 also has a shorter time to peak. It reaches that peak in a much shorter time than 2 and 1. And all of these 3 responses are bounded by the exact same, I didn't draw it so great, but they're all bounded by the exact same settling time. Okay. Let's look at a line of constant time to peak. So now we're going to look at this response. So as we move in this direction along constant lines of time to peak, what does our response look like? It looks like okay. Very poorly drawn, but notice that all of these 3 functions peak at the exact same time. All of these 3 functions all have the same natural frequency. They all have that same frequency. But all of these do not overshoot the same, right? This one overshoots more. So that would be, this one overshoots more than this one, and this one. If we do 1, 2, 3, we got 1, 2, 3. This one overshoots more, and 1 also takes longer to settle. 3 overshoots the least, right? 3, the overshoot is the least, and 3 also, because it's further this way, has the shortest settling time. But again, the time to peak is going to be the same for all 3 of these. They all have that same frequency. And lastly, let's look at the case of constant percent overshoot. So a system with constant percent overshoot, the poles are going to look like this. So as we travel along these lines of constant percent overshoot, what happens to our system? This is 3, 2, 1. All of them have the same percent overshoot. But what's happening here is 3 has the shortest time to peak and also the shortest settling time. 1 has the longest time to peak and also the longest settling time. So again, in general, the response of 3 is typically a better response, and more ideal response in most cases, is going to be a better system response than the case of 1, and all of these maintain the exact same percent overshoot. A lot of times when we're dealing with control systems, if we want to fix everything, if we want to have everything if we want to have a better everything, better percent overshoot, better settling time, better time to peak, that sometimes requires an exorbitant amount of power. So a lot of times what we're left with is we have to make design trade-offs of, well, we get to pick 1 or 2 of these parameters. We get to optimize 1 or 2 of these and sacrifice the last one to make our design decisions. This is a way, looking at these pole locations, that you can sort of pick, where do my poles need to be in this system to get the ideal system response I'm looking for. Thanks for watching, everybody. Have a great day. Like, subscribe, smash that like button, okay? Subscribe, share.